This is gonna be an interesting day.
The girl would be like, no, he's dead in the class.
Guys, pay attention, please. What's the conversation? Go outside if you want to have a conversation, please. The birthday girl doesn't speak English, so she'll never understand that, but the rest of you can.
I remember liquids and solids aren't included in the expression.
Deal with aqueous reactions.
Aqueous are included.
Right. Also working number 5 where there's 2 carbon monoxide on both sides of the expression. You know the same as how can you say it's a reaction?
CO2 on the right hand side. Right, so for those of you that forgot this too here, please put it in. Right? I wrote it, but you missed it. I erased it and wrote it in darker letters. How's it going, Wolfson? Not good? Why? It's horrible. You're late to class? No. Oh, you're late to something else? Good. Okay, guys, you are expected to know these. You're going to have a couple of these on the test, okay? So, yes, you're going to have easy questions like this on this class. That's why this class is easy, yes? Not challenging for most of you. So, gas or liquids or aqueous, what is this? These are gases. Products divided by reactants, yes?
Yes, sir.
So the pressure of O2 raised to the third power, that's a product. Yes or no? Divided by the pressure of O3, which is a reactant, raised to the second power. And that's it. You got your points for that question. Of course, it's not going to be that easy. The second one is the pressure of, it is a gas, the pressure of NaCl raised to the second power divided by the pressure of NO raised to the second power, because that's the coefficient, divided by the pressure of CO2. And that is raised to the first power because the coefficient is a 1 in front of that. Yes or no?
Yes.
Okay, this is in aqueous, so should we write pressure?
Yes.
No, concentration.
Does not have a pressure, so for aqueous, we're gonna write concentration. And concentrations is brackets, yes? Concentration of Ag, NH3, 2 plus, raised to what power? Raised to the first power, yes? Because the coefficient is a 1. Divided by concentration of Ag plus, divided by the concentration of NH3, raised to the second power. Were you here last class? I don't remember you being here. I do remember when you missed class, guys, okay? And you have been missing lots of classes.
I've been watching your video.
I
You
don't
can
want you to watch
verify
the
that.
videos. I want you to come to class.
Yeah.
Because if you guys start missing class, I start putting the videos. And that's not what happens, okay? Most of you come to class. So what's it for this one? Hmm?
This is pressure of carbon monoxide.
Pressure of
Carbon monoxide.
CO raised to what power?
1
To the first power. And the pressure of this, yes? Pressure of H2O, yes?
No.
No? This is a liquid, so it's not part of the equilibrium constant.
Yep.
So you omit it, it's gone. The pressure of CO2 and the pressure of H2. For this one, we have a solid here. Is that included in it?
No.
Nope.
Solid is not included. The rest of them, oh, there's another solid. It's not included. So it is the pressure of CO raised to the second power divided by, oh no, the pressure of CO2 raised to the second power divided by the pressure of CO raised to the second power. For this one here, equilibrium constant, concentration of SN2 plus. What's next? This is a
Get
gas, so we
pressure.
have no choice but to put the pressure
Hydrogen
of
gas.
that gas
Yeah.
divided by the concentration of H plus raised to the second power. Guys, is that difficult?
No, sir.
That is
very
not difficult. I write a question like this on the test, I'm giving you 3 points, yes? What type of thinking does that require?
easy. 0.
I mean, you can teach this to a 5-year-old kid, okay? And they can do it right on the test.
So what do you do with this equilibrium expression?
You will find out soon enough, my friends. Calculate the equilibrium constant, right? The purpose of the equilibrium expression is to find the equilibrium constant. And what is the purpose of finding the equilibrium constant? Well, knowing when the reaction is at equilibrium. And how does that help you knowing when the reaction is at equilibrium? I don't know. Ask a pharmacist. They will tell you.
And you said that the equilibrium constant doesn't have units, right?
Does not have units, no. Determine the value. Sometimes you hear the value or the magnitude, or just the equilibrium constant. So whether it says the value or the magnitude is the same thing. So I want the equilibrium constant for that. And I have
So this is just like Hess's law?
well, not
Yeah.
like Hess's law, but yes, like Hess's law.
Yeah.
Ah.
Seems
Not
very
like
similar.
it, but like it.
What's it supposed to mean?
It means that you don't do what it is for Hess's law, because this is not Hess's law, but it's similar in some aspects, yes?
Yeah.
So if it were the same, it would be called Hess's law. Okay?
Same
You
concept.
try to do the problem, and then I'm going to show you how to do it. This is something we did already. This is called manipulation of the equilibrium constant. So, like Hess's law, you're supposed to add these two equations, yes? And these two equations are going to give you the other equation that you are looking for, okay? Unlike Hess's law, in where you added the enthalpies, here you are going to multiply the equilibrium constants. That's unlike Hess's law. That's why it is the same, but not.
Okay.
Okay, if you don't know, you can ask the person next to you. See if they know. If you both don't know, that's because you don't learn in my class and you didn't learn in 1045. Your phone is discharged at 8 o'clock in the morning, isn't it? What you do the whole night? Not charge it?
Yeah.
You slept talking to your boyfriend?
No.
It's horrible.
I slept under the pillow.
So it can give you cancer, huh? All the radiation coming from the phone.
Professor,
Yeah.
didn't you say one time though that anything but a low visible radio is less harmful to you? You know what I mean? Like it's less harmful to you.
Yes. Yeah.
Isn't it like super minimal?
Yeah, but there is probably some type of radiation that is getting out of the phone that we don't know much about, that is constant into your ear, that it might be messing up something inside. I don't know. My guess is that the battery has energy inside, yes? Probably the battery is releasing some type of radiation, which may, over time, give you something back.
Could it have to do with the signal of the cell phone and connection to the satellite?
Radio waves, most of the time, don't cause a problem.
Okay.
But
Even if it's like, because it's like, it's not a strong wave, right? But it's constant so that you have it. Is it because maybe it's so close, like closely concentrated to you?
it could be, I mean,
They really should do research on this. I mean, it's such a common thing.
when people start having cochlear cancer in the ear,
How about the Bluetooth headsets?
might be better.
I heard that they were worse. Any other? Barely.
Okay, guys, ready?
No, I mean the proof.
Okay, look, I'm gonna show you first. This is how you should do this. And this is actually very easy. Some of you might find it difficult if you go through the whole thing, yes? You only concentrate on the reactants. You don't have to worry about the products. You concentrate on the reactants. And you check the products afterwards. HF, is it a reactant or a product in the reaction that I want? It is a reactant. Here's HF. Because there is only HF on one side and only on one equation. This HF should be a what? Reactant or a product? Reactant. It should be a reactant. Now when you look in front of this HF is, I need to have what in front of this HF? I need to have a 2. So I'm going to multiply this by 2. And this will be 2H plus 2F minus. What did I do to that equation? I multiplied it by 2. What am I going to do to the equilibrium constant? Multiply times 2 is incorrect. Because this is not Hess's law. It is because the coefficients mean what, guys? The coefficients mean multiplication or powers. We did this last time. Why are you depressing me?
So you're gonna rise it to the.
You want a quiz on Monday? You don't want a quiz on Monday?
Of course,
Oh,
yeah,
it's easy.
sure.
Alright, it's gonna be 50% of your grade. So if you miss it, you're gonna get a 0. See you on Monday. So, the equilibrium constant, since I multiplied everything by 2, I am going to raise it to what power?
Squared.
Second power. That is raised to the second power. Now the other reactant that I have is C2O4 2 minus, yes? Where is that at? In the other equation it is a what? It is a product, and I need to make this a reactant. So what do? I reverse this equation and I write C2O4 She brought the chicken.
Oh my god.
Is that the chicken?
No.
Oh, man.
Don't tell me Ms. Rodriguez wants to eat that chicken today. That's her birthday wish.
Their birthday present. Chicken on a platter. Man, that's funny.
Okay? So, what did I do to the equation?
You flipped it, so you changed the sign.
I reversed it, yes? So what do I do with the equilibrium constant? Inverse. And the inverse of this is...
1 over anything?
Inverse is 1 over something? Okay? Now I add both of these up, and I should get the product. Did I have to do the products for this thing? No, I didn't have to do the products. I only did one thing. So, 2HF, yes. And this is when I double check. 2HF. 2H plus, does it cancel out with any 2H plus?
Yes.
Yes, it is a reactant here and a product on another side. So that cancels out. So 2HF plus C2O4 2 minus will give you 2F minus plus H2C2O4. Now, because I added both of them, what do I do with the equilibrium constants?
Multiply.
I multiply them, yes? I mean, we just multiply this times that. Okay. Did you have to do this to get to this here? You didn't have to do it, so if you're in a hurry, in the MCAT or the PCAT, you don't have to do it. I'll show you in a second. So, the equilibrium constant for the first one, 6.8 times 10 to the minus 4 raised to the second power times, you multiply the other one, as I inversed, it was this. What's this number?
I got 0.12.
.12?
Yeah.
How's that, guys?
Fair enough.
What was the difficult part? Adding both of these equations? So here is, if you don't want to go through all of this, yes? Because this will take you time, yes? So if you don't want to go through it, this is how you do it. You are just going straight to the equilibrium constant, and you are saying, well, I need 2HF to be on the what side? On the reactant side, yes? I look at this HF, is this on the reactant side or on the product side? On the reactant side, but what does it have in the front? I have multiplied this one by how much?
2.
By 2. What do I do with the equilibrium constant?
Rise it to the second
I square.
power.
So you just do it right here, right now. You square. And it's going to be multiplied by the other one. And then you go here, C204. Where is that at? This is a product. What do I do with this equation?
Flip it.
I find the inverse. That's what I do. I multiply it by the inverse of that, which is 3.8 times 10 to the minus 6. And the answer is 0.12, and I did not have to rewrite the equations, none of that. This is the correct way of doing it. Once you do it 20 times, then you can do this in your head, or you don't need to do it, and you just do it this way. If you do it this way, I think on the test that you cheated, right? Because you didn't show me all your work. Because this is not the NCAT or the PCAT, I want you to show me. Okay? So you can know it both ways, just use the long one in my class. You want one like that on the test?
Yes.
I mean, I don't know what's hard about this chapter. It looks like all this chapter is easy stuff. Everybody gonna get an A. I don't even know what this stuff is. I recently wrote these problems you see on this paper here 10 years ago. So you're talking about fresh chemistry here, my friends. Okay. At 472 degrees Celsius, the following gases were analyzed to be. Is it called analyzed or analyzed? This is not called vacation, it's called vacation, yes? Oh no, this is not an English class, right? 7.38 ATMs for H2, 2.46 ATMs N2, and 0.166 ATMs NH3.
Is that 160 or 166?
What?
Is that
166.
166. This, I don't know.
It's like a 6 to me.
Okay. Thank you.
So calculate the equilibrium constant.
That chicken, man.
What Where's the chicken at? Oh, it's inside of that towel.
Freaking big now compared to before.
You saw it?
Yeah.
At the end of class, you gotta put it in the thing so I can say equilibrium on chicken.
I don't know what's waking up.
Oh my god. You guys are so loud.
It's a he, right?
Yeah.
It's a rooster.
That's gonna wake you up in the morning. Man, I would kill it. I love animals, but if that thing starts doing that in the mornings, oh my. Woo. Your neighbors are gonna kill me.
What does the temperature have to do with it? What does the temperature have to do with it? Why do you use the temperature?
Because the equilibrium constant changes with the temperature.
Is there an equation for this? Or?
I don't. I'm sure there is.
Okay? Ready?
Yeah.
He asked right now, why is the temperature here? Do you use this temperature for anything so far? No, you don't use it. You use it because this experiment was run at 472, and you always have to tell what temperature you ran an experiment at. Okay, whether you use the temperature or not. Okay. So we're calculating the equilibrium constant for this. The equilibrium constant is products divided by reactants, yes? Pressure of NH3 raised to the second power divided by the pressure of N2 divided by the pressure of H2 raised to the third power. You agree, yes or no? Well, yeah. Divide and multiply by this, but divided by that. So, in order for us to calculate the equilibrium constant, what type of numbers can I put in there?
Pressures.
Yeah, pressures, but when?
Depending on the state.
At what point? At the beginning, at equilibrium,
At equilibrium.
past equilibrium, when?
At equilibrium.
You put numbers in here that are at equilibrium. How do you know numbers are at equilibrium? Well, if they tell you that they were analyzed, okay, that is at equilibrium. Anything that reads that word, it's at equilibrium, okay? Because you can't do it before equilibrium. So, these numbers are when? At equilibrium, so I can put them in here. Do you know what numbers they started with? No, you don't know what numbers they started with. But those are the numbers after equilibrium was reached. Yes? So, we're going to write it here. Pressure of NH3, where's NH3 at?
0.1
raised to what power?
squared.
Second power. Divided by the pressure of N2. Where is N2 at? 2.46. Raised to what power? The first power. And the pressure of H2 raised to what power?
Third power.
Third power. You plug those numbers in, what do you get?
I'm liking this so far.
Don't worry, I calculated these 10 years ago. I got you, okay?
You can math will change over time.
Man,
There you go.
math is prehistoric. It's crazy.
How's that?
Dinosaurs are doing it.
9.13 times 10 to the negative third.
So far, so good. It's pretty easy.
Oh, I'm stupid. What is an exponent?
Does it have a name? What? What? What's the most common?
Mario.
Don't tell me you caught him shady.
Holy shit. I eat so many of them though, so.
Guys, questions about this?
Nope.
No questions?
Are you always going to give us some numbers in equilibrium?
No, not always.
What?
How would we solve for it?
Okay, but that's the next problem, but I'm not always going to give it to you at equilibrium. I'll give you one problem, which I give you equilibrium numbers.
Okay.
Then the next problem is I give you initial information and one equilibrium number, and then you got to do something else to find the equilibrium numbers.
Then can you give
Okay.
us an example?
Yeah, I'm going to give you an example.
It's always going to say analyze.
No. It's not always going to say analyze, no. Okay, let's do another one, okay? But is that clear? You have equilibrium numbers, you plug them in, that gives you the equilibrium constant. If you don't have equilibrium numbers because I did not give them to you, what do you have to do? Find them. That's what you have to do, find them. You got that, Ms. Rodriguez? Because you're looking everywhere, you're daydreaming in my class, girl. What's wrong with you? Yeah, me, I don't think so. Here's another fresh problem. There is, that is an equation, and I tell you,
He's gonna give us a concentration of 1.
a 5.00 liters of a 0.124 molarity ammonia solution.
Okay.
Showed calculate the equilibrium constant. It has battery. Check.
Yeah. You just lost a bar.
What?
You just lost 1 bar.
When I said that, huh?
Hmm?
You're afraid of it.
I think the trick to this is that he's giving us concentration of the solution. So. He's giving us concentration of
Okay, so what did I just give you here?
concentration of the solution.
I give you initial concentration, yes. This is how I made the solution with ammonia. And I am giving you this OH minus. When is that? Is that at equilibrium or is that initial?
Well, it's a product, so it can't be initial.
I could add it. I could add it too.
I think that's the equilibrium.
It is equilibrium. What tells you that it is equilibrium?
The brackets.
The little brackets?
No.
So that says
Because
concentration.
if it's initial, it's little brackets too.
Showed.
Showed, okay? Because here, I said I have this, yes? And showed means that after I have it, I looked for it and I analyzed it. But the word is not now analyzed, yes? That's what he was asking. Now the other word you add to your list when it says showed, it is, or another word is determined. It means at equilibrium, okay? Yes or no?
Yep.
If you see words like a flask was charged with this, or this was added to the flask, what's that? Initial or equilibrium? Initial, okay? So here, there are 3 things. The equilibrium constant, let's say, initial, let's write it inside, okay? Initial information and, look, let's not do it like that, let's do it like this. Should we do it like that?
Yeah.
No, because you'll get confused with kinetics, yes?
Well, I get it, but
You don't get confused with kinetics if I write initial there?
Yes.
Look, let's write that. Initial and equilibrium. This means initial what? Concentration, and that means equilibrium concentration. Whichever one of those three you are missing, and you are given the other two, you are going to perform the same mathematical, let's say, operations. So if I have the equilibrium constant and I have initial, can I find the equilibrium concentration? The answer is yes, you can. If I have the initial information and equilibrium information, can I find the equilibrium constant? The answer is yes. If I have equilibrium information and this stuff, can I find the initial information? Supposedly, yes? That will be a little tougher, since you can begin with many different choices. That's not something I'll ever ask you. I'll ask you one of these two, yes? And if you have these two and you're looking for the other one, you're going to do something called an ICE chart.
I heard of this before.
Yes? ICE. You ever heard of it before?
Yeah.
What does it mean? ICE, that's what ICE means? Initial change in equilibrium? I don't think so. ICE is what you make in the refrigerator, yes? By freezing water. Okay? So, here's how we are going to build this ICE chart. You are going to rewrite, and an ICE chart is a table showing you concentrations of reactants and products. So an ICE chart is going to look like a table. And that table will be divided into three, what are those called? Rows or columns?
Columns.
Rows or columns. Whatever, okay? You divide this thing into three. 1, 2, 3. And in the first one, you're going to have what type of information? I, which stands for initial information. Next, you are going to write C, that stands for change. And E, that stands for equilibrium. Yes or no?
Yes.
In there, we're going to write the information that we know. Do I have any initial information about NH3?
Yes. 0.012.
Yes, I have it. It's given to you at the beginning. 0.0124. This is in molarity. What's the concentration of H2O? Hello? Concentration of H2O is about 50 molarity. Yes? In dilute solutions. You don't need to know. Because it is a what? Look here.
Liquid.
It is a liquid. Because this is a Mickey Mouse class. We don't use anything. We just disregard this. Don't worry about it. NH4. Do I have any NH4 that I began with?
No.
No, I do not have any NH4, and the reason why I don't have any NH4 is because it doesn't say I have any NH4. Yes? How about OH minus? Do I have any OH minus?
No.
0. That will change in the future, but it doesn't change now. So I didn't tell you anything about those. It's not there. This information here for 8OH that I have, is it initial?
No.
This is not initial.
That's not
It's
equilibrium.
not initial. This is equilibrium. So that's the end over there. But we're not going to worry about that yet. Let's talk about the change. If you set up reactants, what do you expect the reaction to do? Go forward or reverse?
Forward.
Forward, right? So the change in concentration, should it be a bigger number or a smaller number from here? Smaller number. So the change will be negative. So I'm going to write minus x.
I thought it was
You thought what?
I thought you were supposed to you have to multiply the initial, like negative initial.
You thought wrong.
I thought wrong.
Well, if you go and watch those videos from the,
That was
what
like
is
2
it,
years, like 2 years ago.
Crazy Academy, you said? Okay, so you have to use the coefficient here in the front. If this would have been a 2x, I mean a 2 here, you write a minus 2x here, yes or no? If they are products, they get a plus. And what is this change? Plus x. Is it the same x as that is?
No. Oh no, yeah.
Yeah. If you decrease this by 2, this thing here only comes from that, yes? So if I decrease that by 2, this increases by 2. So plus x. How about this one?
Well, that's plus whatever the final concentration is.
Guys,
You
the
get-
change here is a plus x.
Well, why isn't it plus the number you get in the end?
Because that's equilibrium.
What do you mean plus what number, what n?
Because it says that at equilibrium you have 4.6 whatever.
We're building the chart. That's what it is. This is a change, yes? You don't know what the change is, so it's x.
But it starts at 0, it has to be that number.
But you don't know what it is. You gotta write an x somewhere. That's like saying, I am not gonna put an x in an equation because I know what it is. Can you do that? Or you write an x in an equation so you can solve for that x, right? Yes or no? In the change, what letter are you always going to write? X. And if it is a reactant, it will get a minus. If it is a product, it is going to get a plus.
And
Period.
the coefficients go.
There is no thinking about this, around this, none of that. Okay? If it has a coefficient here in the front, you're going to use this coefficient here, yes? Because it will decrease by 2. Because 2 of them are reacting to disappear, yes? But not in this case. Now, at equilibrium, what you are going to have is this plus this and write it down there. Yes or no? So you're going to have 0.012 minus x. What is it going to be on the other side? 0 plus x, which is just x. And here is 0 plus x, which is just x. Do not find a shorter way. Do not find an easier way. This is the only way.
We're not going to put the bottom right corner under hydroxide, the concentration though,
We are.
and instead of just the X there.
No. This
Because
is
that's the
building.
equilibrium.
This is building the ice chart.
Okay.
That is the way you build it. That's it. It's done. Yes? Now, in order for you to find the equilibrium constant, what do you need? You need the expression, yes? What is it? Products divided by reactants. So the concentration of NH4 plus times the concentration of OH minus raised to the first power, both of them, yes? Divided by the concentration of NH3. Yes or no?
Yes.
Now, in order for me to find the equilibrium constant, what type of numbers do I need? I need equilibrium numbers. That means that I have to find what this x is, yes? So, I have to have given you some type of information about equilibrium, yes? And I did. I gave you the concentration of OH minus. Here's OH minus. Here's the equilibrium for that. Whatever is here, is that clear? Whatever is here is equal to that number. It just happens to be very simple. Yes or no?
Yeah.
If that number would have been 0.12 plus x is equal to that number, yes? You got to find x from there. Yes or no? This is where, if you think the way you were thinking, you'll make a mistake here. That is a number at equilibrium, but I need to find x. Okay? And it's very simple when x is by itself here. If this would have been 2x, what do? I gotta solve for x, which means I gotta divide this by 2. If this would have been 0.013 plus x, that's equal to that. Whatever you have here is always equal to the number I give you.
Okay.
And then you gotta solve for x. Yes or no?
Yep. Got it.
This is why you finish the ice chart with the x's and then find what you need. Of course, now that you found the x, now you're going to plug it in everywhere, yes? So here's another x. This is 4.6 times 10 to the minus 4. Is this another x? This another x. 0.12 minus 4.6 times 10 to the minus 4. What does that give you?
Which one? 1.15. 36 something. Which one are you looking for?
I forgot to put a 4 here, yes?
Yes, you did.
We're in 0, 1, 4. What is it?
1.1523 times 10 to the negative
119?
2. No, 1.15.
1.15.
No, that one.
1.19 times 10 to the negative second.
Where are you guys looking at?
No, that one is the number. Is the number.
Guys, you're confusing me, okay? 0.0124 minus that number. What does it give you?
The number.
Okay, very good. He made another mistake. And now you're using the right calculator. Yes? Before you had a smart calculator. So, do I have the numbers now at equilibrium? Yes, I do. So what do? I plug them in here. Equilibrium constant is NH4. What's the concentration of NH4 at equilibrium?
4.64.
Okay? 4.64. 4.64 or 4. Oh yeah. It's 10 to the minus 4. Now here's what some people like to do. Some people like to say, oh, square. I don't want you to do square. Okay? Did I do square here? Did I do this square here? No. I wrote the concentration of this. What's the concentration of this? That. And then I write the concentration of this. It happens to be the same. I don't want you to simplify it by saying it is square. Because what is going to happen is you're going to get used to saying, oh, square, square, square. And when it's not square, you're not going to remember it's not square. And now divided by NH3. How much is NH3? 0.0119. So the equilibrium constant for this is 1.81.
So you get 1.80.
You get 1.80.
I got 1.8.
What? I don't believe you.
Yeah, the same as I plugged in.
So 4.64 times 10 to the minus 4 times 4.64 times 10 to the minus 4 divided by 0.0119 gives you 1.80.
1.8 times 809, so you just want it to make it the 1.81.
So I'm right?
Yes.
Or I was right 10 years ago? Even if I'm wrong, I'm not changing it. What happened?
I was right too.
You were off by 2?
No, I was right.
Oh, you were right?
Yeah, man.
I doubt it.
I look
Okay, guys? Yes?
That's cool.
How did you like an ice chart?
There we go.
Now, I'm going to give you a warning. You ready? I'm going to give you a warning. This chapter has baby ice charts. You're going to have baby ice charts on the next test. The chapter after that is about ice charts. The chapter after that is about ice charts. So you're going to have ice charts on the next test, on the third test, and on the final exam. So basically 75% of this class has been ice charts. My opinion is you learn how to do it now. Okay? Whatever amount of time it takes you, you learn it now because it's going to get worse.
It gets
Okay?
more complicated.
It gets more complicated. But not more complicated than that, you just have different numbers in there. But it's the same ice chart with different numbers. Yes?
You do with acids too, right?
I give you what?
You do that in the acids chapter too.
You do that in the acids chapter, you do that everywhere.
Yeah.
Okay? Some guy in my class at the end of the semester says, oh, finally, I learned ice charts for the final exam. And I go, what a waste. Learn ice charts now?
It's really not that difficult.
Nah. Everything is easy, guys, yes? Everything easy, yes or no? Everything is cake.
So far, I like this chapter better than the last one. How can you tell? There's no way. Not big enough for me to determine the weather.
Three exams during class and final exam. Okay, let's talk about something called reaction quotient. Guys, reaction quotient. The reaction quotient is the same expression as the equilibrium constant expression, with the only difference that the reaction quotient is calculated when you don't know it is at equilibrium. Okay? Yes? Because if it were at equilibrium, what would it be called? Equilibrium constant. And you can still calculate Q in order to determine if the reaction is at equilibrium or not. And then, depending on whether it is or not, then you'll know if the reaction is going to do either go forward or reverse. So let's say that I have an equilibrium constant of 4. Yes?
Okay.
And it's the same expression, yes? So I calculate Q. Do I know if it was at equilibrium or not when I calculated Q? No. This could be initial information. You never put initial information here. You can put initial information here. And let's say that I calculate this, and the reaction quotient is 2. What needs to happen? Is it at equilibrium? When Q is equal to 2, is this at equilibrium? No, it's not. It will be at equilibrium when it reaches what? 4. So what has to happen to the number as you go from 2 to 4? What has to increase, the top or the bottom?
Top.
I don't know, you guys are the ones stalling.
No, it's top.
But look here. If you don't know, yes? 10 divided by 2 is how much? Kind of tough, right?
Super.
And 20 divided by 2, is it a number bigger or smaller than this?
It's bigger.
20 divided by 2. It's a bigger number, yes? So as this number on the top increases, yes, the number increases. So in order for me to go from 2 to 4, I need to make what increase, the top or the bottom? The bottom.
The top.
Right? The bottom decreases?
No. You're tricking us.
Yeah, the top isn't tricking you. Does the bottom decrease for that number to increase, yes or no?
Yes.
It could.
It could be either way.
Okay, this is for the mathematical wizards in this class, yes? So, if the number on the top increases, the number increases, yes? Very good. Let's say that I leave this number on the top the same, and the number on the bottom decreases. What happens to this number? Put in the calculator, my friends, because you don't know. You don't know.
It's bigger. Yeah, of course you divide it by smaller.
What happens?
It's
bigger. It gets bigger, yes?
Yeah.
The bigger the ratio, yes?
Yeah.
That's okay, you all put it in the calculator, that's good. So, two things, right? Either the number on the top increases, making the number bigger, or the number on the bottom decreases. But in a relationship, that one is bigger than this one in comparison, yes? So, how do you go from Q is equal to 2 to equal to 4? What needs to increase, the products or the reactants? The products need to increase. So when Q is less than the equilibrium constant, the reaction goes forward. And the reaction goes forward until equilibrium is reached. Yes or no?
Okay.
And equilibrium is reached when? In this case?
At 4.
When it gets to 4, yes? If it doesn't get to 4, it's going to continue wanting to get to 4. Sometimes it can't do it. Now what happens if Q is greater than the equilibrium constant? You'll have too many products, yes? So now the reaction needs to go where to make this number smaller? It needs to go to the reactant side, yes? So you're going to say the reaction here, reaction goes reverse. And what happens if you calculate it and Q is equal to Keq?
It's at equilibrium.
Reaction at equilibrium, very nice. So tell me, from this explanation, what is the reaction quotient used for? Violeta, what do you think, my friends? She's Violeta too, don't worry. I'm going to call you Violeta from now on.
Yeah, that's the reaction thing.
You like that?
I like that.
Yeah. That's her back there. She's shy. What is the reaction quotient used for, guys?
Determining whether or not the reaction is at equilibrium.
To determine whether the reaction is at equilibrium or not, and once you do that, then what? You determine if the reaction is going to go forward or reverse. So, reaction quotient is used to determine if the reaction is going to go forward or reverse. So if I give you initial stuff and I ask you, determine if the reaction is going to proceed forward or reverse, or predict whether the reaction is going to go forward or reverse, what do you have to calculate? The reaction quotient. Didn't get that, did you?
Yes, I did.
So let's say I mix things in a flask, and I want to know if what I mixed is going to make the reaction go forward or reverse. What do I need to calculate? The reaction quotient. Once I calculate it, I can compare that number to the equilibrium constant number, yes? I have to have the equilibrium constant number. So it is a comparison. From initial information, can I find equilibrium information if I have the equilibrium constant?
Say it again?
From initial information, if I have the equilibrium constant, can I find equilibrium information? The equilibrium concentrations?
Yes.
Yeah. Yes, I can. Using what? Using an ICE chart. So, when you calculate Q, you can find the concentration at equilibrium using an ICE chart. But if I ask you to predict what it's going to do, you don't have to do an ICE chart, yes?
Okay.
You just find Q. Yes or no? Yeah. You want a problem like that?
Yes.
Yep.
Why? You want a problem of everything?
Yep.
You know, I'm not supposed to do any problems in this class. I'm just supposed to go through the PowerPoint, blah, blah, blah.
Yes, I know.
Go home, that's it, right? Why are you
That's
guys
what they do at
making me work?
Wilson. You know it's true. There never be problems at Wilson. Never. They'll be like PowerPoints.
Okay, the equilibrium constant for this is 51.
51.
51. Now that I think about it, I should have taught organic one.
Yeah, you should.
Can you change
But it's
it?
too late now, so it doesn't
Are
matter.
you doing it?
Can you change it? Can you change it?
No, no, I don't know yet.
What?
I'm not doing it in the fall. I'm not doing it in the fall for sure. But I'm gonna try for the spring, okay?
Yes, man. Yes.
Then the spring teacher is gonna go. Are you gonna be able to teach organic too?
Organic too, it depends. I'm gonna try, because I like you guys. Because if you took 1045, who took 1025 here with me?
I came in.
So it's possible you can have me for 1025, 1045, 1046, organic 1, organic 2.
Yeah.
We be cooking some meth for sure.
Oh, shit. That's what I'm talking about.
Like guys, there are better professors out there. You just don't know them, right?
He's a man. That's what you're looking at here.
No, let's not. Let's do this another way, okay? Let's say if a flask was charged with, and even if it's a gas, I'm gonna give you a concentration, okay? How much time do we have left? Not much, you said? 20 minutes. Not much. Yeah, that's true.
Fast flies, man.
So predict how the reaction will proceed to reach equilibrium at 448. Why is the temperature there? Because the reaction was ran at 48. If a flask was charged, a flask charge means what? That you put that
Initial.
stuff in it, yes? Maybe I should give you pressures. Okay, look, let's change it, okay? I feel bad about this. No, it's not the same thing.
In that case, would you have to do PV equals RT?
Not the same thing, okay? When it's a gas and it's if it's aqueous, it's not the same thing. Sometimes it happens to be the same number, sometimes it's different.
Well, in that case, would you have to do PV equals
Yeah.
RT?
It is not the same thing. One is called Kc per concentration and the other one is called Kp. It just don't make a difference. You can go from one to the other,
Okay.
okay? I'm not teaching you the difference yet. I may or may not. Since these are gases, yes?
Mm-hmm.
I feel bad giving you a concentration even though on the test, whatever I give you, that's what you use, okay? But let's put pressure here, okay? Pressure looks better, yes? The pressure of HI is 0.592 ATMs. The pressure of H2 is 0.296 ATMs. And the pressure of I2 is 0.88 ATMs. I just woke up and I'm tired already.
Story of my life.
You have too much energy? Because you've been drinking coffee?
Red Bull.
Red Bull? You wake up and you drink a Red Bull?
Are you serious? Oh man.
I have a mini fridge and just open it up.
Once you get them ulcers, and then you're gonna be like, damn.
Tell me guys, what do we do here?
It's not a joke.
Because it's asking us to predict, yes? Is it asking us for the equilibrium constant? No, we already have the equilibrium constant. Is it giving us initial information?
Yes.
If it asked us for equilibrium concentrations, can we do it?
Sure.
For equilibrium concentrations, can we do it? Yes, we can. How?
With an ice chart.
With an ice chart. Is it asking us for an ice chart? Is it asking us for equilibrium information?
No.
No. It's asking us to only tell you whether it's going to go forward or reverse. So simple. I'm going to calculate Q. And Q is exactly the same expression as the equilibrium constant. So the pressure of HI raised to what power? Guys, what power?
2.
Second power. Okay, yes, raised to the 2. It's fine. Divided by the pressure of H2 and divided by the pressure of I2. I just plugged those numbers in.
Yep.
Pressure of HI, and don't be looking at the board and doing it. Look at your paper, do it, and just listen to what I say. HI is what concentration? I mean, what pressure? 592 raised to the second power. Divided by the pressure of H2, 0.296. Okay? Also divided by the pressure of I2, which is 888. Is that raised to any power? No. So Q is equal to 1.3? Yes?
You're using the word properly.
You're what?
You're using the word properly.
I can't hear you, man. You got something in your mouth. What did you say?
You're using a pretty bad calculator right now.
Using a bad
Yeah.
calculator?
Use that calculator.
1.13.
No,
No, I didn't use that calculator. Yeah.
No, it's good. I want you to make sure that what you're putting in is what you think it is, so you can use it.
I got 1.3.
What is it?
1.3.
1.3?
I got 1.1.
Confirm.
Miss Rodriguez,
You repeat
you look disengaged. What your problem is?
It's her birthday. That's the problem.
Because it's your birthday, you don't pay attention, right?
Yeah.
Because the day of my birthday, I paid attention.
But is it, if the KQ is already like already like past a certain number, it's always going to go in that direction, right? Like if it's really small, KQ is really small, it's going to go
KQ? No. The KQ only means the ratio of products to reactants. It doesn't mean it's going to go forward or reverse. It's just going to go to that number. Whatever happens to be.
But
Maybe there's more reactants, maybe there's less reactants. Besides the point. It's going to go reverse? No. It's going to be mainly reactants. Go reverse. It's not going to go reverse if they only put reactants. It doesn't matter how small it is. It's going to go forward. Okay, so and mainly it could be, most of it could be reactants. Most of it could be product.
Are we comparing Q to the Keq?
So, guys. So, Q is 1.3. Is it bigger or smaller than that?
Way smaller.
It is smaller. The number wants to be what number?
51.
It is 1.3 and it needs to go all the way up to 51. How does it do it? By increasing the products or the reactants?
Products.
The products. So the reaction is going to go forward. Reaction goes forward. Yes? And we can use an ice chart to find those numbers. But the ice charts have different levels of difficulties. Now, do you guys know how to do the quadratic equation?
Yep.
You know how to do the quadratic equation?
Yes.
Okay, very good.
I don't
You're
think
gonna
you
do
can.
it.
You can't pass algebra without knowing that. Like, you do like 3,000.
Okay, the question is, how long does it take for you to do the quadratic equation? 25 minutes?
No, like 2
Like
seconds.
a minute.
And in 2 seconds.
In this calculator, it's gonna be a pain though. I have to admit. You gotta like square root and then do it.
Should we talk about Le Chatelier's principle?
Yes, Le Chatelier. Let's go.
You got 5 minutes?
Huh? We have 5 minutes? We don't have 5
We
minutes.
have 10 minutes.
We have 12 minutes. According to my watch. And some of you guys were here 10 minutes late today.
You were
You were late.
That's right, some of us.
Okay, so let's do this, okay? This is called Le Chat Liar's Principle.
Another French dude?
Another French guy, yeah.
Yeah.
Back when French was cool. Isn't it Le Space Chatelier?
Okay, guys. Yeah, I don't speak French, so I say Le Chat Liars.
It would be Le.
So, Le Chatelier's principle
Chatelier.
says,
That's
guys, pay attention. Write this down. Le Chatelier's principle says. Okay, let me talk to you first of all, Le Chatelier's principle. Don't write anything down. When somebody tells you, I am at equilibrium, what do you see?
Tranquility.
Someone tells you equilibrium, what do you picture?
It's like,
Do you picture a dog fighting
no.
with a burglar? Is that what you think? Right? You don't think. What do you think?
A dog having the burger.
A dog having a burger, that's not equilibrium.
Don't stop moving.
So, let's say you are sleeping, yes? When you are sleeping. Not that you're not at equilibrium when you're sleeping, but let's say you are because you're at peace, you're not moving, you're not the usual annoying person. So, if someone disturbs you, what do you do? You're at equilibrium and someone disturbs you, what do you do? Someone tries to wake you up, what do you do?
Yeah,
You're trying to equilibrium.
In the middle of the nicest sleep, what do you do? You might punch him in the face,
Yeah.
And all of that you do because you want to do what?
Return to equilibrium.
Go back to equilibrium. So, this is what happens. You try to counteract the disturbance. Whatever they're doing to you, you want it done with so you can go back to what you used to be. So write this down. When a system at equilibrium is disturbed, when a system at equilibrium is disturbed, that is you sleeping, somebody tries to wake you up, it counteracts the disturbance. That word is very important. It counteracts the disturbance.
That's like if you add something in the reaction to make it throw it off, then you have to counteract it.
Yes. So it counteracts the disturbance by either going forward or reverse.
The chicken likes that.
Oh, we gotta put the chicken on it.
You're gonna take it and put?
No, not me.
So you're gonna?
It's you.
I'm allergic.
It's like you said.
He doesn't want to get like.
You have to grab it.
Not me, I'm sorry. I can't touch that chicken.
Chickens are pretty dirty. Yeah, usually they're dirty.
Actually, they can more loud.
So, let's say this is the system at equilibrium, yes? And a disturbance, write this down. Disturbance are changes in concentration. Disturbance is a change in concentration, pressure, volume, or temperature. So if I change the concentration, did I disturb the system?
Yep.
Yes. If I change the pressure, did I disturb the system?
Yep.
If I change the volume, did I disturb the system?
Yep.
If I change the temperature, do I disturb the system?
Yep.
Yes. Basically, the system is disturbed, but whatever you do to it, except if you just look at it, yes? If you look at it, nothing happens.
So it's the PV equals nRT variable.
What? No. Nothing to do with that. So, ready? If I add B, I am going to say, I increase the concentration of B. I added B to this system, yes?
Yeah.
Hello?
Yep.
What does the system try to do to my disturbance, which was at B? It tries to do what to B?
Add more C.
It goes for.
Not rejected, it has no choice, okay?
It has to consume it.
I put it. So what is it going to do? The system is going to decrease the concentration of B. It does not care what happens to A or to C. If you increase B, it just wants to bring B down. How do you bring B down? By using it, yes? By using it up. So the reaction will go what? Forward. Because if you go forward, the concentration of B goes where?
Down.
Down. What happens to the concentration of A as the
down.
reaction goes forward?
It goes
It
down.
also goes down. What happens to the concentration or the pressure of C as the reaction goes forward? It goes up. But the system doesn't care. It just wants to stop this amount of B from being in there. So let's say you decrease the concentration. So if you increase B, I'm going to say the reaction goes forward. And that means forward. So this is shorthand, okay? So I don't have to write so much. If the concentration of C goes down, what happens? The reaction does what to C?
Concentration goes down.
You bring the concentration of C down.
Then it's gonna go reverse.
What does the system try to do?
You bring it back up.
Bring it back up. Make more C. How do you make more C? Going forward or reverse?
Backwards.
Go forward.
Guys, if I take away C, it has to make more C. The only way to make C is by going forward, yes? Going forward makes C, uses up these two. Going reverse makes these two, uses up this one. So, if I decrease the concentration of C, the reaction goes forward to make more C. Because it needs to be used up. B needs to be used up. And it's used up if it goes forward. If it goes reverse, B is not used up, you make more B. The concentration of A goes down. What does the system try to do to A?
Increase the concentration.
Increase the concentration of A. The only way to increase the concentration of A is by going where? If you go forward, you use them up. It goes reverse. Because reverse makes A and B. And it wants to increase A, so it goes reverse. Okay, bring the chicken, okay? Because you guys are tripping on this equilibrium thing.
It's like an inside joke of our class.
Who is in the mood for some chicken wings?
Damn.
I think this is our mom.
Grab it.
It's not coming out.
Chicken is gonna crap all over the place.
Yeah, he will. Oh my god, film that.
Grab it and put it here.
Oh shit. Oh, that's hilarious.
Wow, it's unfair. Dropped everything.
Right? Just let it go.
I think it's gonna move.
Don't do that. Wait, bring it a little up.
Bro, you're scared of a chicken? Like, come on.
Really?
I just don't want to be in the camera when the chicken is in the camera.
Bring it forward. Like it's
But put his face.
You gotta say it.
Okay, good.
Equilibrium and chicken, right?